do one more example. Let's suppose that we take an independent random sample from a normal distribution. We're sampling from a normal distribution, but we just don't know the mean and we don't know the variance, sigma squared. But we are pretty confident that we're sampling from a normal, okay? And we'd like to use the maximum likelihood estimation method to estimate the mean and the variance, okay? So here we go. So let's find the maximum likelihood estimator for the mean first. Whoops, this is a mu. Sorry. Okay, so our likelihood function. Remember, since our sample is taken to be independent, it's just the product of those conditional density functions, really. So it's all of this stuff raised to the nth power, and then I need to multiply by the rest of it. K equals 1 to n. E raised to the negative, what's the formula? Yk minus mu squared all over 2 sigma squared, right? Okay. Just using the density function for a normal with mean mu and standard deviation sigma squared. Really, all this is just the density function, right? Multiplied in times, but subbing in the actual observation values there for the variables. Okay, so now let's go ahead and take the log of all of that. The log of the likelihood function then is so this first part will give me n times the log of 1 over root 2 pi sigma. Okay, and then plus remember the log of the product is the sum of the logs, right? Log of all this stuff is just going to give me the exponent, negative yk minus mu squared over 2 sigma squared. Okay. Now at this point, I can go ahead and take. So actually, you know what? Notice that actually, I'm going to put a sigma in here too. This likelihood function, it depends on sigma and mu, okay? It's really a function. I want to treat it as a function of sigma and mu. I want to find the values of sigma and mu, okay, that maximize this likelihood function or log likelihood function. And so I'm going to differentiate with respect to mu. Okay, I'm going to use the curly D's there because I know that there's another variable I can differentiate with respect to. So d mu of the log of the likelihood function is going to be, let's see, there are no mu's in this first term, so that's going to be a 0. Plus, let's see, if I differentiate all this stuff with respect to mu, I get sum k equals 1 to n negative 2 yk minus mu, and then times a negative 1, right? All over 2 sigma squared. 2's canceled, those negative signs cancel. All of this stuff is just equal to the sum, k equals 1 to n, of yk minus mu over sigma squared. Now, set this all to 0. Okay. This implies then that, I guess this just means that the sum of the yk, k goes from 1 to n, is equal to the sum, k goes from 1 to n, of my maximum likelihood estimator for mu. Now, what do we have here? This is this sum is just equal to n times those. Right? I'm summing up. I'm adding this up n times. That's n times this, right? So all this implies that my maximum likelihood estimator for mu is in fact 1 over n times the sum of my values. Okay, nothing new there. It's the same thing as our regular old friendly neighborhood unbiased estimator. It's the sample mean. So it turns out then the sample mean is not only unbiased in every case for every distribution, but it's also, in the case of the normal at least, it's the maximum likelihood estimator for the normal. Now, what about the variance there? So let's go back to our log likelihood function and differentiate this guy now with respect to sigma. Okay, so d sigma of the log likelihood function. That's going to be negative. Let's see. It's going to be negative n times the derivative with respect to sigma of log sigma, okay, plus I'm going to differentiate all this stuff with respect to sigma. It's going to be, okay, it goes from 1 to n. We get a 2 times yk minus mu squared over 2. Well, this is over 2. Sigma to the negative third, right? Okay, so I'm just differentiating this same log likelihood function, but this time with respect to sigma. And now, if I set this equal to 0, setting to 0, what does that give me? Oh, whoops, I didn't quite finish. What's the derivative of this? This is going to be negative n times 1 over sigma, right? Okay. So if I set this all to 0, I get that n over my maximum likelihood estimate for sigma equals 1 over my maximum likelihood estimate for sigma cubed, right, from here, times the sum, okay, goes from 1 up to n of yk minus mu raised to the 2th, right? And multiply through by this, then we see that in fact my maximum likelihood estimate for the variance, then I get this squared, is actually, it's 1 over n times the sum. Okay, it goes from 1 to n yk minus mu quantity squared. So what does this say? This is pretty incredible, actually. The maximum likelihood estimate for the variance, the maximum likelihood estimate for the, maybe we should say the square of the maximum likelihood estimate for the standard deviation there is actually 1 over n times the sum of squared deviations from the mean. Not 1 over n minus 1. Remember the sample variance. The sample variance is taken to be 1 over n minus 1 times the sum because it's unbiased. The maximum likelihood estimator for the variance when you're dealing with a normal is 1 over n times the sum of square deviations. Okay, that's important.